Thank you for joining us live for this special astronomy-focused Ask the Expert Q&A hosted by the STEM faculty at the Open University. My name is Dr. Natalie Starkey and I'm the Public Engagement Officer for the School of Physical Sciences here at the Open University. And today I'll be chairing this session where we'll be hearing all about stars, black holes, gravitational lensing, and how you can get involved in doing this science yourself from your own home. Now, shortly, I'll be putting your questions to our fantastic panel of astronomy experts here with me today, and I'm going to let them introduce themselves in just a minute. They're going to each give a short introduction about their work before we launch into the Q&A part of the session. Now, if you'd like to submit a question to our panel, then please do email us at STEM, that's STEM, -news @open.ac.uk. This session is being recorded live and will be available on YouTube and Facebook afterwards. Please check our social media channels for more information. So without much further ado, I'm going to let our panel of astronomers introduce themselves.
Hi there, my name is Heidi Tiemann and I'm currently finishing up my PhD at the Open University. So I work on variable stars, binary stars, and a bit of citizen science. So that's what I'm going to be telling you about in just a few minutes' time.
Hi, my name's Stephen Sargent. I'm a professor of astronomy at the Open University. I'm interested in extragalactic astronomy. So these are galaxies beyond our Milky Way, right down into the early universe where we can see galaxies being born. And I'm also interested in gravitational lensing. This is looking for warps in space and time, and also on how we can bring machine learning and artificial intelligence to extragalactic astronomy.
Hi everyone, my name is Beatrice Mingo and I am a postdoctoral researcher within the astronomy group here at the Open University. I am also an extragalactic astronomer and my main interest is black holes and jets, which is what I will be telling you about today.
Okay, thanks everyone. So I think we're going to kick off with Heidi's presentation. You can hear all about what she's doing for her research before we move on to the other two. Take it away, Heidi.
Okay, so hopefully you can see my slides there. But as I said, I'm Heidi and today I'm going to be talking to you about super-WASP variable stars and what that all means and how you can get involved as well. So let's start the story with the super-WASP telescope. And super-WASP was the wide-angle search of planets, a project designed to search for exoplanets around other stars. And it's actually been the most successful ground-based search for transiting exoplanets to date, having discovered over 200 exoplanets. But as I'll show you in a few minutes, it's actually had a really big impact on other areas of science as well. And so you can see this telescope here on the left isn't a normal telescope. It doesn't look like your typical tripod with your tube and your lens on the end. It's actually a telescope which is built of a robotic arm with 8 cameras on which survey the night sky. And there's actually 2 of these telescopes, one in the Northern Hemisphere in the Canary Islands, observing the Northern Hemisphere night sky, and one in South Africa, observing the Southern night sky. But together, both of them worked for 11 years to observe the night sky night after night, year after year, to build up an amazing picture of what we have above us. So in the image on the right-hand side, what you can see is a kind of sky map which shows you where super-WASP observed. So the blue and black areas of the skies where super-WASP didn't observe many stars, but the green, red, white areas, that kind of creepy sort of smile across the middle there, that's actually where super-WASP observed more stars, and that's the Milky Way itself. And you can see that some patches of the Milky Way super-WASP just didn't observe because essentially there's too many stars, the density of stars is too high for the pixels of the cameras in super-WASP to resolve individual stars. But even if it didn't observe all of the Milky Way, it still managed to observe 31 million unique stars in the night sky, which is incredible. So what can we do with all that data? We've been observing the night sky night after night, year after year for 11 years, which means we've got an incredible bank of data about stars and planets. And if we look at the brightness of every star in every image over the entire time we can observe it, we can build up a really good picture of what that star is doing. So for example, that star in the middle there, highlighted in green, if we look at the brightness of that over time and plot it, over the 7 years we've observed it, you can see in the graph on the right, we can see that the brightness changes a little bit, but it's hard to tell on that 7-year timescale. So if we zoom into a month and then just a few days, and then just even one night on its own, you can see that something really interesting is happening. And the brightness of that star is actually varying really regularly. And this is what we're really interested in, the variability or regular changing of these stars. So when we talk about variable stars, what we essentially mean is that the stars vary in brightness. So once you know about the name, it's quite self-explanatory. And these types of stars we normally categorize into two broad categories. So intrinsic variables, where some sort of internal physical change is causing the brightness of the star to change, or an extrinsic variable, where something external from the star actually seems to affect the luminosity of the star. So the brightness of the star doesn't actually change, but some of the light is blocked, so it looks like it's changing from our point of view. So let's have a look at some of those individual types, because they're really quite interesting. So if we start off with pulsators, these are stars which expand as they heat up and they get brighter, and then they collapse under the force of gravity. And they do that over and over and over and over on periods, maybe just a couple of hours or even months at a time. And if we have a look at the plot of the brightness against, or the time against brightness, then we can see that the star has this sort of asymmetric profile where it increases sharply in brightness and then decreases gently again. So we watch out and look at the brightness of a star and it seems to be doing this, we can tell it's a pulsating type of star. Similarly with a binary, these types of stars orbit one another. That's an extrinsic variable. And contact binary stars are stars which orbit so close to each other that they actually share some sort of common envelope of star stuff, which means that the brightness of the star isn't changing, but as they orbit, one star blocks the light from another, so it appears like they're changing. So you end up with sort of M or W shaped light curve, which is, it depends on how you look at it, M or W. And then another type of star is a rotating star. And this is, well, all stars rotate in some sort of sense, but you might be more familiar with this from our own sun. And on our own sun, we actually see sunspots, which are darker, cooler patches on the star's surface itself. And as the star rotates or the sun rotates, they get dragged around. And that appears to show that the star is getting dimmer and brighter. And so we look at, again, a plot of brightness against time. We can see a sort of more triangular or sinusoidal shape. So if we have a look at essentially just the plots of brightness against time, we've got an amazing idea of the astrophysics behind every single star, just from a few simple measurements. So in our department, we've had some amazing discoveries before. The one on the left is called a post-common envelope eclipsing binary, where it's thought that there could be planets orbiting binary stars, a little bit like Star Wars and Tatooine. In the middle, we've got some auroral Lyrae stars and Blasco effect stars where they don't just change, but the amount they change by changes. So there's so much change going on in these systems. And on the right, one of my favorite systems was discovered by a colleague called Marcus Law, and he actually found 5 stars orbiting one another, which is just incredible. So you can see there's a huge amount of data that can come out of SuperWASP. But the issue is, how on earth do we find the real and interesting and weird stars from those 31 million stars that SuperWASP observed? We can do a bit of machine learning, but we've actually gone down the route of using people, citizen science, because actually humans are really good at detecting the individual and small and weird and interesting changes. So that's why we started the SuperWASP Variable Stars project. We have 1.6 million light curves of variable stars, which were taken from a program which my supervisor ran called Andrew Norton, and he's not the program, the supervisor, of course. But he's popped these all on the SuperWASP Variable Stars project, and we ask you to essentially look at a light curve and tell us what you think it's doing. It's a pattern matching exercise, so matching a light curve to an astrophysical kind of change, really. And through that, we can identify what all these amazing stars are doing. So we're looking for things which might be changing on longer or shorter periods to what we're used to. We might be looking for stars which are doing weird things, like they've got 2 periods or they've got 2 classifications. If we find a binary which has a pulsator in it, that's an incredibly interesting thing to astronomers. They can be really, really useful. Also looking for stars that don't really fit the categories we're used to. And we're looking for big populations of stars. You can imagine if we find tens of thousands of stars doing the same sort of thing, we can do essentially some sort of census of the stars and work out more about them. But so far, we've had around 1 million classifications from the public, which is fantastic. And we still have many millions to go. So we would love your help if you want to classify a few of these. But some of the things we've identified so far is that a lot of the light curves are junk. And that's absolutely fine. It's fine to find data which is rubbish and then find it and go, actually, you know what, that's not useful. We're going to put it to one side and focus on the interesting things. So we found around 30 to 40% of stars in our data set are interesting and useful. And out of those, we found some really interesting things. One of my favourite ones was picked up by some citizen scientists, and we think what they've discovered are these new types, or this new configuration of giant binary stars, where these two giant stars are orbiting so close they're touching one another, and this might mean they might merge and explode and cause a beautiful light echo, a little bit like this one on the screen here. So that's something that citizen scientists have discovered, which is amazing. And something I'm really excited about, I just went through a load of the data last week, and we've actually identified over 500 previously unknown variable stars, which is great because that can feed out into the wider astronomical community, and people can use that data and that knowledge in their own research, and amateur astronomers can also use it. So I'm going to finish there and pass on to Stephen in just a second, but here's the link if you're interested, and I think we'll put them below. So if you want to get involved and classify some variable stars and find your own, then please do. Thanks very much.
Thanks, Heidi. That was really, really interesting. I love all those beautiful images you've got in that talk. Yeah, all the links should be available in the chat shortly. We're going to move on to Stephen now, if you're ready to go.
Yep, let's see if I can share the screen and get this working. Share. And click. There. Now if I get rid of that. Can you see my screen? Is everything okay? Hello? Can you hear me?
Yeah, we can hear you. It's all looking good.
Marvelous, brilliant. Okay, so I'm going to talk about warps in space and how warps in space meet artificial intelligence. So I'm quite interested in gravitational lensing, and this is where you have a foreground galaxy and a background galaxy almost perfectly lined up along your line of sight. And you see the background galaxy through the warped space of the foreground galaxy. So it's illustrated in this schematic diagram here. We've got a background source and a foreground deflector. And we see the background source through this dink. And in fact, you have two lines of sight here that you can reach the background source. So I think maybe this is better illustrated as an animation. So I'm going to first put up a picture of a background star. Okay, so here's a background star. Okay, and what I'm going to do is I'm going to put a foreground galaxy in front of this background star, and I'm going to crank up the mass of this galaxy. So the gravitational lensing gets stronger and stronger and stronger. I'm going to make this galaxy transparent so it doesn't get in the way of the view. So we do that and slowly crank up the mass of this galaxy. I'm using real gravitational lensing software to do this. And you see, well, you see what happens to the background star. And in fact, there's some real physical lessons in this because we're using real gravitational lensing software here. And that's, well, one thing is as the image stretches, it doesn't get fainter. So you can make a background object look brighter because of this foreground curvature in space. And also there's multiple images. So you see Paul Brian Cox now has two mouths. He's got a mouth at the bottom and a mouth at the top. And that's a real effect in gravitational lensing. So you can have multiple images of background objects. So let me now show you instead a real gravitational lensing image. And this is the galaxy cluster Abell 2218. It's a foreground galaxy cluster, and the orange splodges are elliptical galaxies that exist in this galaxy cluster. And I don't know if you can see these sort of archy features, these curves. These curves are background galaxies seen through the warped space of this foreground galaxy cluster. And from the stretching and the curvature, you're actually visualizing the curvature of space and time. It's an amazing image. Now you can use these magnifications and these warps in all sorts of very interesting ways. So for example, here is a recent gravitational lens image, it's taken at a wavelength where you can't see the foreground galaxy. You've just got the background galaxy, and it's warped into a ring around the foreground galaxy, which will be at the center. Now, the research team here have worked out where this light will have been coming from, deprojected it and unlensed it, and you find actually a surprisingly regular galaxy. And looking at the motion of the gas in this galaxy, you find actually it's very smooth. It's like a rotating disk galaxy, like our Milky Way, which is curious because at very early epochs in the universe, you expect a lot of star formation to be clumpy and blobby. So this system is telling us something very interesting about star formation and the growth of galaxies, the formation of galaxies. So this is one of the great uses of gravitational lensing, is it gives you a window onto very early phases of galaxy formation and evolution. And this is sort of, well, this was the state of the art about 10 years ago or so. This is a gravitational lensing survey called SLACS, the Sloan Lens ACS survey, and it's of order 100 or so strong gravitational lenses. And the yellow splodges here are the foreground and the blue are the background galaxies. But this is going to change radically in the next few years, because there is a space telescope coming called Euclid, and it's got a primary mirror, a main mirror, only a bit smaller than the Hubble Space Telescope, and it'll be mapping about half the sky. So it'll be getting images of about half the sky to almost Hubble Space Telescope quality. And because of this, it will be able to spot those rare lensing configurations where you've got a foreground and a background galaxy lined up and you see these characteristic curves and dinks. So it will be an amazing machine for finding these gravitational lensing events. So to give you a visual impression of what that will be like, we start off with the way things were a few years ago, and this will be the picture that we'll get. What you're supposed to see here is basically 100,000 tiny little gravitational lensing events as I've just rendered onto one screen. So we will be awash, hundreds of thousands, in fact, of gravitational lensing events. But we will only be able to do this if we can find those beautiful lensing configuration images among the billion galaxies, other galaxies that this space telescope is seeing. And so we've been trying to develop artificial intelligence to try to sift through these billion galaxies and select and identify just those rare events where you've got a background and a foreground galaxy lined up. And so we've got some simulated images, because the Euclid Space Telescope hasn't launched yet. We've got some simulated images here of that we use in our machine learning training. And so we've held competitions. We've pitched one sort of artificial intelligence against another sort and try to find the best artificial intelligence that can find these warps in space and time. And we've made 100,000 simulated images. But in this competition, there was one team, one valiant team, led by Neil Jackson. This is Neil at Jodrell Bank. And what they did is they visually inspected every single one of these simulated warps in space and time, and identified which ones were the warps and which ones were not. So it was a humongous effort to do this. And these are world-leading gravitational lens experts here, okay? But the astonishing thing is, they did not win. The machines did better than the world experts. So this was a real shocker. It was a real shocker for me, certainly. So why? Why did they not win the challenge? You'd think the humans would be better. So perhaps it was because they had a small amount of time they could do this, so they got tired. Maybe they got tired. So we could test that, because there is a very big, very active citizen science community who have become very skilled at spotting these gravitational lensing events in data. So we thought, let's try asking the citizen scientists and see how they do it and see whether they can beat the machines. So we ran a citizen science experiment called Euclid Challenge the Machines, taking simulated images and seeing if you can spot where the gravitational lenses are. And I've got a picture here of the challenge. It's now completed. We've run out of subjects to classify, and the result was that still this experiment would not have won the challenge. It would not have beaten the artificial intelligence. Humans, we can't find humans that can beat the artificial intelligence. It turns out actually there's something humans do a bit better, and that is that the gravitational lenses that came out, that are identified by humans, are much more reliable. So you have a much purer sample of objects than machines can create. But also it's a much smaller sample. So, so where is this going? So we would like to understand what it is that humans are seeing and what it is that machines are seeing. So because human vision and machine vision are obviously doing something really fundamentally different. And so I'd like to introduce you to another citizen science experiment called Galaxy Zoo Clump Scout. And this is asking volunteers to analyze other sorts of astronomical data. The idea is to find the places in distant galaxies where stars are forming. I've got some images from the Hubble Space Telescope here, and what it's asking people to do is look for these clumps and identify where the clumps are. So this is where stars are forming, this is where the galaxy is building up its stellar mass. This is how a lot of star formation goes on in the early universe. So that gravitational lens I showed you at the beginning, where it was a very smooth rotator, that's very much the exception. So one reason I'm showing this to you is that we've got, at the moment, a very simple machine in the background that is trying to understand what humans are doing when they're classifying, when they're identifying the clumps. And so it's doing this in real time. And in due course, we're going to ramp this up to an artificial intelligence backend that tries to learn, tries to replicate what humans are doing with their machine vision. So then the question is, can machine vision, can artificial intelligence completely replace humans? And I think the answer is definitely no. So here's an example of why I think the answer is definitely no. So if you asked a machine to find the faces in this image, it would dutifully report all of the different faces in the image, but it would not say, there's a clown in the middle, okay? So humans have this capacity to just take a step back and unask the question that machines just are nowhere near having the capability to do at the moment. So I think at the moment, and foreseeably, there is still a need for humans to be looking at data, because humans can say, wait, that's weird, in a way that machines just can't. So when you're looking for gravitational lenses, you could say, wait, that one's weird. That one doesn't look like the others. It looks like it's got two foreground galaxies and it looks like a face. Okay, and no machine would be able to tell you that at the moment. So I think there is still an important need for humans to be looking through data. And in the meantime, though, I would recommend that you have a go at the citizen science experiment, Galaxy Zoo Clump Scout. And that's everything I wanted to say, and that's the link.
Thank you, Stephen. That was so entertaining. No, that's absolutely amazing. I'm really gunning for the humans. I'm like, come on, we can do this. And we're going to move on to Beatrice next, if you're ready to go.
Yes, let me share my screen. Can you see that?
Yeah, that's fine.
Fantastic. Welcome everyone again. I'll be telling you about some of my favorite objects in the sky, which are black holes and jets. I'm hoping you will like them as much as I do. If that actually wants to play. Oh, there we go. So black holes, fortunately, are a much better known concept now because they've been in the news fairly recently. So they probably sound fairly familiar to you, and you might think of them as a fairly modern concept. But the idea of something that is so dense that light cannot escape it has actually been around since the 1700s. These two gentlemen here, Pierre-Simon Laplace and Jean Michel, conceived this idea independently because science communication at the time wasn't obviously as fast as it is now. To make a black hole, essentially, what you need is a large amount of gas. A large amount of gas that's big enough that you can create a high mass star. You just put that gas together, let it collapse into a star, let it evolve for a few million years, let it go supernova, and if you have enough mass there, the collapse of that quantity of mass of that gas will not be stopped by anything, and it will eventually turn into a black hole. If you have something slightly less massive, it will make a neutron star. If you have something that's similar to our sun in terms of mass, you will create a dwarf. So for good or for ill, our sun is not going to make a black hole at the end of its life. But fortunately, that also means that it's going to live much longer. The lower mass the star, the longer lived it is. There's two other possible ways that you can make a black hole. This is the main way that we know about. There's two theories. One says that we actually created primordial black holes at the beginning of the universe, shortly after the Big Bang. These would have been tiny, and they would probably have evaporated by now through something called Hawking radiation. And there's also something called black hole seeds. This is something that we are resorting to explain how black holes can grow to something as big as the black holes that we see in the centers of galaxies. Some theories postulate that you cannot just grow stellar mass black holes, the ones that you create through this common mechanism that I have just explained, to make something that is as big as the ones that we find in the centers of galaxies. So we need to go from something that's less than 100 times the mass of the sun to something that's tens of thousands up to tens of million times the mass of the sun. And as far as we know, there's only two ways in which we can build this process. One is through accretion, so the black hole actively eating matter around it, gas, stars, things that eventually just fall in and increase its mass, or through black hole mergers, which you probably know about now as well because of the LIGO-Virgo results, the gravitational wave detections a couple of years ago. But essentially, these are the two processes that we have observed can build black hole mass and get something that is formed from just a single star to these huge masses that sit in the centers of most galaxies and regulate some of their dynamics. You're also probably familiar with a picture of M87 here on the top right corner. I hope you can see the detail of how big that black hole is. You can see the tiny, tiny orbit of Pluto for scale in the center of it. What you can see there is not the black hole. The black hole is actually sitting in the middle because nothing can escape the black hole. What you see is the light from things around it. Black holes are ninjas, and if they don't have anything around them, it's actually very hard to see them. The only way you can see them is through their consequences. So this little video here is made out of 16 years worth of observations of the stars in the center of our galaxy. And you can see them wobbling and twisting around and just jumping all over the place. This is because there is an invisible mass in the center. These things are orbiting around. There's just pulling and tugging at these stars. You cannot see the black hole. You cannot see anything around it, but you can see that it's having an effect, that there is a mass there that's pulling the stars. And that's because our galaxy is actually fairly quiet. It's not actively accreting at the moment, the black hole in our galaxy. But we know that it has been more active in the past, that it's had some really lovely meals a few million years ago. We can see this by observing at frequencies that are not the visible light. For example, you can see the picture here on the left is from the Fermi telescope. This is a discovery from 2010. And you can see this is looking towards the center of our galaxy. So you can see the plane of the Milky Way in that slightly flattened, bright and dark disk. And you can see these two bubbles, these two structures that rise perpendicularly from it. This is the result of our black hole having a medium-sized meal a few million years ago. These are called the Fermi Bubbles, and they're about 25,000 light years in size. So when the black hole accreted some gas, it also managed to erupt some of that gas around it and form these two structures. And we have discovered recently, actually only last year, from using the telescope MeerKAT at radio wavelengths, that there is a smaller pair of bubbles closer to the central black hole, and you can actually see some of the magnetic fields in the center of our Milky Way as well. These two bubbles are about 1,400 light years in size, so a lot smaller than the ones discovered by Fermi, and they're also a lot younger. But as I said, our Milky Way's black hole is actually fairly quiet. It's not doing much at the moment. There are black holes out there which are a lot more active. We call those active galactic nuclei. Excuse me. And when those black holes are accreting gas, they have a big reservoir of gas around them. The energy they produce through this accretion is enough to make them outshine the entire galaxy they live in. This is how much energy is involved in this process. So on the little diagram on the left, this is just to show you that these structures I'm showing in the big picture in the background are concentric. Essentially, it's like a pancake surrounded by a donut. If you want, it's just expanded into 3D so you can see it more easily. We have the black hole sitting in the middle, which you can see here. If you see my cursor at next to that cloud of blue stuff, and then the gas that's around it, as it gets closer and closer to the black hole, it heats up through friction, and it heats up so much that when it reaches the areas immediately outside the black hole, it emits X-ray light. If you go slightly further away from it, the gas is a bit colder, and you can see that emitting optical and ultraviolet light. And even further and further away, the gas gets colder and it gets a bit puffier, and you can observe that in the optical, then infrared, mid-infrared, and eventually far infrared. But these are not the only phenomena that exist around black holes. As I mentioned earlier, we also have jets. This is what happens when the magnetic field that is present in this gas gets twisted, gets wrapped around, that's what we think at least, in the area close to the black hole. You can picture it as water going down a drain. The way it gets twisted, it gets warped. And when these magnetic field lines get very tight, very close together, this very hot gas that dissociates into nuclei and electrons gets accelerated by these magnetic fields, and it gets launched at speeds close to the speed of light. So just to give you an idea, the size of a black hole versus the size of the galaxy it lives in is like comparing a billiard ball to the size of the Earth. So from this tiny, tiny thing that's sitting in the center of a galaxy, you can then launch these super fast jets of charged particles that can reach hundreds to thousands of times distances larger than the galaxy itself. So you can see a picture here in the background showing some galaxies. This is from a Hubble Space Telescope image. And superimposed on that, you see a radio image from the VLA showing these puffy structures, these two jets coming out of a huge elliptical galaxy, much larger than our own Milky Way in the center, and just making their way into the intergalactic medium, just fluffing about and driving shocks into the gas that exists between the galaxies, and just dumping a lot of energy and a lot of matter into that gas. So as you can imagine, these very energetic phenomena are actually very important in determining the energetics and the dynamics of their host galaxies and of the matter that sits between the galaxies. They are a huge influence in how galaxies and the universe itself evolves. So it's very important that we understand them. And this is where my work comes in. My work is about finding out how these jets and how these black holes influence the evolution of galaxies and clusters, much as my mom thinks I'm actually an astronaut because she's not a scientist. So I do this using the Louvre telescope in the Netherlands, which you can picture, you can see on that picture in the center, that little island in the Netherlands that's called the Superturp, and that probably looks nothing like you imagine a telescope to be. So these are low frequency radio telescope antennas, and they actually look like clothes hangers and boxes. But these detect sources in the sky at very low radio frequencies, at very low energies, essentially. And with these, we can picture things like I had shown you before in the VLA image, like the images here on the right. We can picture the electrons that have traveled up these jets. I can also use, for example, X-ray light, as you can see in that orange picture at the bottom, where I can analyze the energetics of a shock that's being driven by these bubbles, by these jets, into the host galaxy itself, that's the Sunspots galaxy. But most of my time, I just look at lots of numbers and lots of tables, and I create lots of plots, as you can imagine. And you might not think that that's very fascinating, but I really think it is. That's where the understanding comes in. We look at the pretty pictures, but we want to understand what the pretty pictures actually mean. Part of the problem is that these jets are very efficient at producing radio light, but they are not. The galaxies themselves are not very good at producing radio light. So sometimes we cannot really tell where this emission is coming from, where the black hole is, where the galaxy is. We can only see the very, very large scale structure. That's why we create contour plots, like the one you see in that top right corner. And that is also where we need people to help. Because, as I said, we cannot see the host galaxies themselves. We can only see these very large emission on very, very large scales. It's actually very hard to put together the different components and to find out where things are coming from and where the black holes sit, which is very important if we want to know how far away they are, how old they are, how they're moving, how they're oriented, and to actually understand these populations and how they influence the universe around them. So humans are still a lot better than machines at finding these patterns and at pinpointing things that are symmetric and at pinpointing where this emission might be coming from. And this is where you can help us. You can see some examples of our Radio Galaxy Zoo projects here on the images. I don't want to spoil the tutorial for you because it's really fun to play through, but you can see some examples of the images that you'll be looking at. For example, you can see a star-forming galaxy here on the center at the bottom. You can see that it looks fluffy in radio frequencies. It's not very bright. It's not very compact. And next to it, you have something like that DLA picture I showed you, where you can see in the contours, because it's easier to tell brightness from contours, same as you would from a map to tell altitude. You can see that there is a core and there are two big fluffy structures. And when you superimpose that on an optical image, you can see, okay, so there is also a dot here that we see as an optical galaxy. That might be where this emission is coming from, where this black hole is actually sitting. So this is where I ask you to please join our project and help us find these ninja black holes. Thank you very much.
Thank you so much. That was amazing. I'm just wondering, I've never used the Zooniverse project before. If I were to go on and go to one of these projects, like how would do I get training? Because it seems like it's, quite advanced and I would know what I was looking at. So how does that work? Do I have to do a training module before I can start kind of get let loose on the data?
I'm going to, my microphone is unmuted. All of these projects have a tutorial. It's the only one. I mean, some of them are self-explanatory. There's projects that cover not only physics and astronomy. Obviously, there's projects in biology. There's some in art, for example. There's some deciphering handwriting from World War II letters. There's something for every taste. And some of them are easier to understand and grasp than others. But all of them have tutorials. All of them have guided steps with examples and images and questions and answers. And they also have an area where you can debate with other people the sorts of things you're finding, any interesting things that perhaps go beyond the project itself.
Do you have any demographics on who is actually getting involved? Like who's your youngest member to kind of help find stars and things? Open to anyone.
I don't know. I mean, we can see who joins on the chats module. We don't get information about age or any personal data, but for people who join in often on the chat module to talk about the objects that they discover or the things they might want to help on. I think most of the ones on my project have been adults, but I've also run this with students in a school, kind of teaching them a little bit about it before. So those ones would have been a little bit younger as well.
That's great. And my final question about this set before we move on to some of the ones we've been sent in is, do you have like a champions list? I was thinking it more in relation to your work, Heidi, because you've got all these 31 million stars or whatever. Do you have someone who sits there all day and just, has characterized, the most?
I did actually look at this data the other day, because you can download who has made each classification as a big data set. And I went through and I counted, I didn't count by hand, but counted how many people, or how many classifications some people had made. And I think our top scorer had made around 70,000 classifications.
Wow.
Which was a lot. So a huge congratulations to them. But
that's
obviously
amazing.
Any classification, even one or two can help. So you don't have to do loads, just one or two can push a project forwards.
Okay, that's really good to know. So some of the questions we've got coming in, so I think we've got one from Emily Smith. She basically had a comment that she just says, black holes and ninjas, love this. I think that's brilliant. And I think you actually answered her question. She was asking about the measurement tool that's most useful in your research. So I think that came in just before you answered that. But do you have anything more to add about that? Because I saw the, the telescope you mentioned doesn't look at all like a telescope that I would normally envisage.
Yeah, radio telescopes don't look like optical telescopes. I mean, you can, as I said, you cannot see the black holes themselves, but you can see the phenomena around them. And you can study those throughout the electromagnetic spectrum. So you can also use optical telescopes to see the gas, the very bright optical emitting gas that I said that sits around them. That's a very useful tool as well. And you can use spectra as well at different frequencies and at different wavelengths to study these things. Or you can use, as I said, images of stars and calculate their orbits and see that there is a mass sitting there. So there's more than one way to study them. For the jets, which are the part that I am interested in, radio is mostly the way to go.
Okay, and then whilst we're with you, we'll just do a couple more on black holes. We've got one from Mark Shawcross. He says, how long does a black hole live for? And it's actually something I was wondering.
So there is something that can cause black holes to die or evaporate, which is called Hawking radiation. It's purely theoretical. It's not something we have been able to measure. But this takes a very, very long time. So the idea is that only the primordial black holes, these tiny, tiny ones that might have formed at the beginning of the universe, will have evaporated by now. So black holes will live much longer than any of us will, and than most things in the universe actually will.
And you mentioned Hawking radiation because we had a question from Simon Austin, who said he read a number of years ago that about Hawking radiation that black holes are actually slightly pink, or is that completely wrong, he says?
Okay. I don't remember. I read A Brief History of Time like 20 years ago, but I honestly don't know at which frequency you would detect Hawking radiation, or even if it makes any sense to explain that in terms of frequency. Stephen, I think, has the answer to that.
Well, it's a black body spectrum is the answer. Okay. And the bigger the mass, it's the colder the spectrum. And so, yeah, really dull red, I guess, for any astrophysical black hole. Colder than the cosmic microwave background, in fact. So nothing can really evaporate for now, but you've got to wait squillions of years into the future before this can really kick in.
And I have a question. What stops a black hole just sort of gathering everything around it and taking over the whole universe? Is it something to do with this event horizon thing, all right? Because this is my really basic knowledge of this stuff.
So people tend to think of black holes as like vacuum cleaners and something that's just sucking at the universe. It's not really that. So if we put the Earth into a black hole, it would be the size of a marble, but it would still have the mass of the Earth. So, if we put the sun into a black hole, nothing would change in our solar system other than suddenly we have no light. The mass itself wouldn't change. So you actually need, a fairly big mass, obviously, to create the traction to drive gas in. But there needs to be something around it for the black hole itself to grow. It's not like a suction. It's just a very compact way of packing mass, like zipping a file, essentially. You just zip a star or zip a galaxy into a very tiny space.
Okay, that helped, definitely. Hold on, we've got lots more questions about black holes. This seems to be the popular topic today. So from Will Rutt, is it possible that there's a small black hole on the outer region of our solar system? I'm not sure where this question's come from exactly. Does that make sense to you guys?
I haven't seen anything in the news or on any papers. I mean, as I said, we can detect these things by the gravitational effect they have. So if there was a mass somewhere in our solar system that was big enough, it would be pulling at something. It would be causing a dynamical effect, and we would be able to observe it. It's very unlikely, unless it was like, the mass of an asteroid that is also, in the outskirts of the solar system, and it doesn't receive a lot of light, so it's very dark. And then would it matter really if it's an asteroid or a black hole? It wouldn't really have any other dynamical effect.
Okay, no, that's interesting. Stephen, we've got a question about your T-shirt. People want to know what's on it.
Oh, it's Rogue NASA. So this was it's okay. A few years ago in the US, there was a ban on some government agencies making scientific statements that could be seen to reflect on government policies in the US. And then there was a movement to sort of rogue social media accounts to disseminate information and do a public service scientific communication. And rogue NASA is one of them. And in fact, this if you buy the T-shirt from the US, they put their profits to a couple of educational charities, one for, I think, STEM education and the other for better gender representation in STEM education. So, which I quite like. So I wear this. So it doesn't really have a context in the UK so much, but it's but you know, have a rummage of the rogue NASA. I think they're a lot of fun.
Thank you. And I have to say, I've been outdone by all the space fashions today. You can't see Heidi's very well. I think you need to show off your jumper. It's amazing. So cool. And you, Beatrice, you've also got stars, is it, or planets or something on your top? Oh, you've also got the earrings. Brilliant. Well, we can't hear you.
Yeah, sorry. I have star earrings and a star top. I wear them to conferences.
It's brilliant. And actually, I'm going to say in the green room before we were chatting, which is, you know, just before we came online on Zoom, yeah, we were talking about how scientists do fashion at conferences and how it can be a bit of an icebreaker at big top scientific conferences if you wear, you know, your best space fashion. Right, let's get back to the science, shall we? A question for Heidi from Will Rutt. Why is our sun not a binary star?
A really good question. I think it's especially good because a lot of stars in the universe, in our Milky Way at least, we know they're in binary systems. So there's various different estimates depending on what type of star you're looking at, but some types of stars, up to 70% of them, might be in a binary system. Doesn't necessarily mean they're close together and touching. They might be quite distant and only affect each other gravitationally rather than actually having any sort of contact and friction there. The reason our sun is, it's probably not something I've thought about that much because you don't really see one. I don't really see Star Wars Tatooine type things day to day. But I mean, I imagine that it's just to do with how our solar system formed. There simply isn't enough mass that we could form two stars. And also, we haven't experienced another star coming through our system and being gravitationally bound to our own. You can kind of have captures of stars. I believe there's some sort of hypothesis which probably goes back to kind of the H.G. Wells type times where there was, I think it was something called Nemesis, might have been a proposed binary star of the sun. Don't quote me on that, it's quite science fiction, but essentially there isn't enough mass to create another star to be around us, really. Okay,
thank you. Is it, I think, Raquel or Rachel word, not entirely sure, one of those two, sorry if I pronounced your name wrong. She asked, what programming tools do you use to do your research? And she's got a few options: Python, MATLAB, or Matplotlib, is that correct? Or R, etc. These mean not a lot to me.
Python.
Python,
okay.
A lot of Python.
Yeah, mostly Python these days. Back in the day, it used to be Fortran. I think some people, especially in the modeling community, that want to do simulations, use C++ a lot.
Okay, so how, I guess if people, Stephen probably knows the answer to this, if you're studying one of the Open University courses, is that covered in that?
Yeah, so we do have a bunch of Python programming in the Open University curriculum. So, I mean, it's necessary because it's such an important tool, and it's also because there's a lot of packages that are built for astronomy that you can and machine learning as well that you can just import in, and it's all done for you. In fact, it's pretty common in machine learning to use Python as well as R. I would say also I should give a nod to IDL, which is a sort of breadboarding tool that a lot of astronomers still use, and I've migrated to Python, but sometimes, well, I've got so much that there's already built in IDL, I keep finding myself switching back, so I have to revert every now and then.
Is Python what you used to warp Brian Cox at the beginning of your talk?
No, that was a standard package I used.
Oh, okay, so we could all play with that. That would be fun.
Yeah, it's called Grav Lens 3, I think, and it's an iPhone app.
Really? Oh, goodness. Hours of enjoyment tonight. Here we go. A question from Tom W. I haven't got his full last name. And I'm not sure who this is aimed at, so any of you can take this one. How stable are planets around binary stars? Probably mostly Heidi, but...
On the whole, probably not very stable. I mean, I may be wrong about this. It's entirely possible. I don't think we know of any planets orbiting a very close binary that's actually stable. They'd normally get thrown off, and that was if they even had the chance to form in the first place. A lot of binaries also are quite unwelcoming environments. Some might be kind of X-ray binaries, kind of spurting out X-rays, which you just don't want to be near. Often, if we are looking for a planet around a binary, the planet would orbit one star, and then that entire system would be orbiting another star. So they'd be going around a bit like that. So we do know of some of them, and kind of previously we've had Marcus Law here at the Open University worked on discovering, I think, around 12 or so of those. So they were quite exciting, and you have to use very precise measurements to detect very tiny effects that the planet has on the orbit of the stars. So it's quite tricky, and I imagine there's probably loads out there that we still got to find.
Thank you. No, that's really good. We have a question from David Arnott. What happened to all the solar siblings formed in the same stellar nursery as our sun? Anyone? I guess the question is kind of referring to the stars, I guess, that were near to our sun when it formed. Have I maybe read that correctly? When he says all the solar siblings formed in the same stellar nursery as our sun.
The problem is we've had so many galactic years that they just spread out all over the galaxy.
So we can't track it back, you're saying, to kind of 4.5 billion years ago?
Not that far, no. I mean, the satellite Gaia is doing amazing things, but that thing I think is beyond the capabilities. But there are people who have been looking for stellar siblings, and people have proposed twins of our sun.
Okay. I had a question about Euclid. Is that hasn't launched yet, has it? Is that launching next year or the year after?
I think about the year after. I mean, it's very hard to prognosticate the future of space launches. In fact, in general, a lot of space missions have been affected by the coronavirus disruptions and so on. So, but let's say in 2 years or so, I guess Euclid will be launching.
And then once it's up there, how long does it take to kind of get up and running and actually giving us data?
Oh, right. So it's got to take, I think, about 6 months to get do its in-orbit checkouts and do the performance verification and so on. In fact, that's quite general with space telescopes, in fact, especially if you're going out to a distant place, like where the Euclid Space Telescope will be going to.
And where is it going to be located in space?
L2. It's a particular spot in the solar system, which is gettable to and quite
stable, I guess.
Yeah. Well, you need to be continually correcting, but yes.
Right. But it's not going to, fall into the sun or something. So that's good.
No, that'd be awesome.
We have a question from, I'm guessing it's not their real name, Geeky Cubed. Does the matter ejected from black holes as jets then go on to create new star-forming regions?
Maybe not the mass from the jets themselves, but as jets drive through the galaxy, they create shock waves. They compress some of the existing gas, so they can trigger star formation within their host galaxies. Absolutely.
Thank you. I think I'm just trying to check back through. Somebody's given a shout out to Professor David Rothery, who's one of their tutors on one of their Open University courses, because they've noted that his fashion sense is kind of out there, which I've got to agree with them. I think it's brilliant. We've got a couple of questions. Simon, I'm not sure if this is a question or a comment exactly, but Simon Austin says, Barrow and Tipler say solar-sized black holes will evaporate in 10 to 66 years. So I guess that's in some paper somewhere that they've read, maybe, and then there's a follow-up, and galactic-sized ones would be in 10 to 99 years. Can you shed any light, excuse the pun, on that?
I don't know the exact timescales, but yes, I mean, that's a very, very long time. Again, consider that we measure at the age of our universe in terms of billions of years. You know, that's 10 to the 9. So to put that in perspective, it's such a long time scale that it is almost meaningless.
Okay, that makes sense. Oh, it's not right. The way, let me check how he's written it. 10. So is it 10 to the 99? Does he mean with that? Okay, sorry, that's me reading it wrong. There we go. Okay, right. I think. Let me check. Have we got any new questions coming in? Yep. Someone from KC. Do you use TopCat software for your research?
All of the time. I love it.
What? Can someone explain what that is?
It's a really amazing piece of software written by someone called Mark Taylor at Bristol. And it's essentially very fancy ways of visualizing astronomy data, tables, plotting sky maps, and also getting data from loads of other databases. You can type in the coordinates of your star, and you can drag in data from across the world and different data sets just onto your computer. And it is, I don't know, I personally use it daily, and I think it's really, really handy. I think a lot of astronomers use it.
Yeah, it's also part of a piece of technology, a wider piece of technology called the Virtual Observatory, which is it's an amazing tool, and it's like one of these Intel Inside things. It's just permeates so much of what we do.
Thank you. And another black hole question. They're so popular today. From Emily Hughes. Does every black hole contain a singularity? And also for me, can you explain to me what a singularity is again?
So the theory goes singularity is like it's a dimensionless single point in space. That's where all the matter that goes into the black hole goes. So if our theories are correct, then yes, every black hole contains a singularity. There's a question, according to some theories, as to whether every black hole has an event horizon or whether some of them are what we call naked singularities. But that is theory. It's actually far more complicated than that. And also, nobody has actually gone into a black hole and taken a peek and then come out to tell us, oh, no, there's actually an elephant in there.
Okay, a question from Will Rutt. Not sure who this is for, so ready for any of you to answer. Can someone explain the time dilation phenomenon around objects of stronger gravity? This sounds like hardcore astrophysics to me. I can repeat the question if you want. Yeah, can someone explain the time dilation phenomenon around other objects of stronger gravity? If you can't, then that's absolutely fine. We know you're just lowly scientists. You don't have to know the world's answers to everything.
I guess what they want to know is, why does it happen? I mean, I can describe it happening as you approach the event horizon of a black hole, and if you throw a watch into a black hole and you're watching this watch tick the ticks will come slower and slower and slower as it approaches the event horizon. And in fact, you would never see it cross the event horizon. But from the point of view of the watch, it's just still going tick, 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 tick. And it crosses the event horizon and just doesn't notice it if it's a big enough black hole. And eventually it'll be ripped to shreds. But it's because there isn't a global agreement on what constitutes the flow of time in relativity. And that's a bit of a fudgy answer, and it's not a great answer because it's not really telling you why that's the case, but it's part of the relative of relativity. It's that your concepts of space and time are relative to your own perspective. Does that help? I'm not sure it does.
It was a very, very complicated question. It's well beyond me. I'm just I'm a lowly planetary scientist. I have no idea what's going on right now. No, I think that definitely helped. I think that might be all we have time for, because let me just check if there's one very quick one. I'm not sure how quick this is, from Ahmed. And the explanation of how I think quasars are still bright while has a black hole in the center, and why it has no jet. Is this a very quick question to answer? We've got about 1 minute.
Right, so there are different types of active galactic nuclei. Some of them have jets and some of them don't. I think that has to do with how fast the gas is falling onto the black hole itself. So the ones that accrete this gas fairly fast don't have jets. It has to do with how the magnetic field around them essentially is wrapped or isn't wrapped, and how the radiation is produced. So it has to do with accretion physics. There's a few equations that govern that. So the ones that accrete slowly or very, very fast have jets. The ones in the middle don't. And the ones in the middle are most of the population.
Yeah, okay, that was actually a much simpler answer than I was expecting. That's great. Well, you guys, I'm afraid that's all the questions we have time for today. I think you'll agree it's been a very informative session. I certainly learned a lot. Just so you all know, a recording of the session will be available shortly on YouTube and Facebook for you to watch again or share with your friends. And all the links are going to be available in the chat, or simply Google Zooniverse. All that is left is for me to thank our amazing panel of astronomers, and also thank you for tuning in and sending in your questions to the panel. Thank you so much. Thank you for joining us live